So our big project for today is to look at eigen stuff. Eigen stuff is not actually an official term for things. It should be kind of obvious. But the stuff is eigen values, vectors, and spaces. So eigenvalues, eigenvectors, eigenspaces. Those are the things that we're looking at here. So I've got a matrix. First column 7, -4, second column 2, 1, and I got a couple of vectors, -1, 2, and 4, 3. So I want to multiply the matrix by each of these vectors because with one of these vectors, an interesting thing happens, and with the other one, the interesting thing doesn't happen. So let's multiply A times U. So we'll take 7, -4, 2, 1, and multiply it by -1, 2. So we're not gonna write all the details. We're just gonna multiply this out. And when we're just multiplying it out, that's when the dot product is how we should do things. So I'm gonna do -7 plus 4 is -3. And 4 plus 2 is 6. So just multiplying with dot products, rows and columns, and we get -3, 6. Now let's look at AV. Or take 7, -4, 2, 1, and multiply by 4, 3. This is going to be more difficult because I picked such large numbers. 7 times 4 is 28, and 6 is 30-something, 34. -4 times 4 is -16, plus 3 is -13. So in the first example, in AU, something interesting happened that did not happen in AV. What happened in AU, the thing that we want to notice here, is that we multiplied matrix A by the vector -1, 2, and we ended up with -3, 6. And what's interesting about -3, 6 related to what we started with? So what's interesting about this particular vector? Anybody notice something? We ended up with a multiple of what we started with, and that did not happen in AV. So in AU, we want to notice that we just ended up with 3 times -1, 2. We ended up with a multiple of what we started with. So the interesting thing here is that the product AU is just a multiple of U. AU equals 3U. We ended with a multiple of what we started with. Multiplying by A just stretched our vector. That did not happen with AV. AV is not a multiple of what we started with. And this is an interesting thing that we want to know about matrices. We like this because we multiplied by this matrix and we just ended up with a scalar multiple of what we started with. So this is interesting. You're just going to have to take my word for it that it's interesting. We have to build up a lot of machinery before we get to learn why this is interesting. But multiplying from a geometric standpoint, we had this vector u. We had a vector u, and AU just ended up being 3 times as long. We stayed on the same line. We stayed in the same space spanned by U. But with V, I know it looks like U and V are going in the same direction. I assure you they're radically different directions. When we multiplied V by the matrix A, we didn't just stretch out V, we rotated it in some other direction. So A times V is not a multiple of V. There's some rotation that happened. in addition to the stretching, because this 34 negative 13 is longer than 4, 3. So some rotation has happened. Instead of just being on the same line as our original vector, we ended up off of that line. Any questions? Okay, so this is what we need to be able to find. What we have here is that the matrix A has an eigenvalue of 3 that corresponds to the eigenvector -1, 2. So in this case, we say A, so matrix A has eigenvector U, which is, I wasn't writing down A, but oh well, and that corresponds A has an eigenvector, which is U, -1, 2, that corresponds to eigenvalue 3. Anytime I multiply A by a multiple of U, I will get 3 times what we start with. So for example, if I take A, let's say 7, -4, 2, 1, because we're thinking of multiplying a matrix by a vector, we're just making a linear combination of the columns of A. And this particular combination, -1 times the first one plus 2 times the second one, ends up just being 3 times whatever we start with. So if I start with some different vector, let's call it out. If I start off with, say, 10 and -20, so I just started off with 10 times that vector U, then we end up with 70 minus 40 is 30, and -40 minus 20 is -60. So we end up with just 3 times what we started with. So anytime we multiply something on the line, -1, 2, we end up with 3 times whatever we started with. Any questions? All right. So -1, 2 is an eigenvector of A corresponding to eigenvalue 3. Since -1, any multiple of -1, 2 ends up being 3 times what we started with, we can say that -1, 2 is a basis for an eigenspace of A corresponding to eigenvalue 3. Since I can take any multiple of -1, 2 and just end up with 3 times what we started with, -1, 2 is a basis for the eigenspace of A corresponding to eigenvalue 3. So an eigenvector of a matrix is a vector such that when we multiply the matrix by that vector, we just get a scalar multiple of the original vector. Any questions? Now you may have noticed that there is a vector that always has this property. And so that particular vector is not going to get to be an eigenvector because it doesn't do anything interesting. It is kind of trivial in that regard. What vector is not going to be an eigenvector ever? What are we not allowed to call an eigenvector? Anybody know while I change pages? Zero vector. The zero vector is not allowed to be an eigenvector because it's always just going to be, we multiply by the matrix A and we'll always get 0. So it doesn't correspond to any particular eigenvalue. So we're going to have to throw that one out. So an eigenvector, let A be an n by n matrix. a non-zero vector is, let's call it U. A non-zero vector U is an eigenvector of A corresponding to eigenvalue. We usually use lambda to represent eigenvalues. So eigenvalue lambda I think I spelled that right. If and only if A times U is equal to lambda times U. So eigenvectors have to be non-zero vectors, and they correspond to eigenvalues, lambda, if and only if A times U is equal to lambda times U. Any questions? So this leads us, A has to be a square matrix, that is correct. So we got to start with a square matrix. So this equation right here, we're looking for non-zero vectors U that have this property, A times U is equal to lambda times U. And so this is going to tell us how to find eigenvalues and therefore eigenvectors. So let's do that. This is the equation that we're going to use to find eigenvalues. So let's look at a matrix and let's find its eigenvalues. So let's let A, I'm going to use the one where we already know one of the eigenvalues and the corresponding eigenvector. So 7, 4, 2, 1. So I want to find the eigenvalues of A. And we're going to just go from definitions or first principles. Let's find the eigenvalues of A. The eigenvalues, we're going to look for non-zero vectors U such that AU is equal to lambda times U. So here's what we're going to do. We're going to solve, oops, gotta switch colors. We're going to solve this equation, AU is equal to lambda U. We're going to have to use this equation to get us some more information. I'm not really solving the equation, am I? Kind of. So let's take off this solve part because now all of a sudden I don't like it. So AU is equal to lambda times U. What we're going to want to do is put this lambda U on the other side so that I can subtract these two things and get 0. And that's going to be important. I want to put the lambda U on the other side so I can get 0, but I can't subtract a vector from a matrix. That's not okay. I can't subtract a vector from a matrix. I'm going to want to eventually factor out the U. So let's first move the lambda U to the other side. So this is equivalent to saying that AU minus lambda U is equal to 0. So by doing this, we can see that we're setting up a homogeneous equation. So if think about all the things that we know, I'm setting up a homogeneous equation, and since U is a non-zero vector, I'm looking for non-zero solutions to a homogeneous equation. So I just set up a homogeneous equation. Yikes. We just set up a homogeneous equation. And we're looking for non-zero solutions. So what is this going to make us think of? We're looking for non-zero solutions to a homogeneous matrix equation. What can you tell me about the matrix? Not the matrix A, but the matrix that's going to fall out of this. If we have non-zero solutions to a homogeneous equation, what does that tell you? So think homogeneous equations and non-zero solutions. What does that tell us about the matrix? It's the columns of the matrix are going to be one of those things. Which one tells us we have non-zero solutions to a homogeneous equation? What are the columns of the matrix going to be? The columns of the matrix should be linearly dependent. And what kind of matrix, what kind of square matrix has linearly dependent columns? What's the big theorem with all the parts to it? Not invertible. So if we have a matrix equation, a homogeneous matrix equation that has non-zero solutions, that means our matrix is not going to be invertible. And so that's going to be our route in to figuring out what these lambdas need to be. But right now, what I want to do is I want to factor the u out, but I can't do that because I can't take a minus some scalar. So we have to do a little bit of algebraic sleight of hand. I can multiply this lambda times u by the identity matrix. And so that's what we're going to do. We're going to multiply the second term by the identity matrix so I can factor out the vector u. So I'm going to write this as au minus lambda, and I'm going to insert the I in here. Lambda I times u equals 0. I'm going to multiply the second term by the identity matrix so that I can factor out the vector u. Multiply the second term by the identity matrix. The reason that I want to do that is so I can factor out the u. I want a and lambda I to be the same size so that I can subtract them. That means I can factor out the u. Right now, in this equation, au is a vector, lambda u is a vector. I can subtract those things. But I want to factor out the u and have a coefficient matrix. That's going to be the not invertible matrix. So we'll multiply the second term by the identity matrix so we can factor out the u. So that a and lambda I are the same size. So we can factor out the u. So now that a and lambda I are the same size, I can write this is just a minus lambda I times u is equal to 0. A minus lambda I is, oops, I gotta scroll, sorry. So I'm gonna multiply the second term by the identity matrix so that a and lambda I are the same size. We did that so we could factor out the u. A minus lambda I is gonna be a 2 by 2 matrix. And since we're looking for non-zero solutions to this homogeneous equation, a minus lambda I is not invertible. So if this homogeneous equation will have non-zero solutions, then a minus lambda I is not invertible. Homogeneous equation with non-zero solutions. means that A minus lambda I is singular. So we've characterized the matrix A minus lambda I as singular. And what that means is the only part from chapter 3 that we need. If A minus lambda I is singular, what does that tell us? So if A minus lambda I is singular, A minus lambda I is not invertible, what do we know about this matrix from chapter 3? The only thing that I care about from chapter 3. What is the determinant of A minus lambda I? Determinant is 0. And that's the thing that we're going to use. So we're looking for, if we want to find the eigenvalues of a matrix, a 2 by 2 matrix A, we're going to look for lambda such that the determinant of A minus lambda I is equal to 0. Oops, that the determinant, whoa, that was almost a mess. We're looking for lambda such that the determinant of A minus lambda I will equal 0. And now we've got to the functional part of the explanation. I just wanted to make sure that you knew that I wasn't just pulling this out of thin air. We want the determinant of A minus lambda I to equal 0. Because that will make A minus lambda I a singular matrix, which means the homogeneous equation A minus lambda I times U equals 0 can have some non-zero solutions. Okay, let's switch pages and see what this looks like. So we want the determinant. We're trying to solve for lambda. We want the determinant of A, 7, negative 4, 2, 1, minus lambda times I, 1, 0, 0, 1, is equal to 0. So this is what we want to have happen. Here's A minus lambda I with this matrix A plugged into it. So I want the determinant of 7 minus lambda, negative 4, and then 2, and then 1 minus lambda. I want the determinant of this matrix, A minus lambda I, to equal 0. Now I'm just going to use my formula for a determinant, which is AD minus BC. So I'm looking for the solutions to 7 minus lambda times 1 minus lambda minus 2 times negative 4 equals 0. We end up wanting to solve a polynomial equation. So we end up with a polynomial equation. Notice that in this case, we started with a 2 by 2 matrix, and we ended up with a degree 2 polynomial equation. We should multiply some of this out. So it's going to be lambda squared minus 8 lambda, right? Minus 7 lambda, minus 8 lambda, plus 7 plus 8 is plus 15. Excuse me. So we get lambda squared minus 8 lambda plus 15 equals 0. We ended up with this second degree equation, a quadratic equation. And luckily for us, we ended up with a factorable quadratic equation. So degree 2 polynomial. So we call this the characteristic polynomial. And it's degree 2 since A is 2 by 2. If A was a 3 by 3 matrix, then we'd end up with a characteristic polynomial that's degree 3, and so on, and so forth. All right, so we end up with the characteristic polynomial lambda squared minus 8 lambda plus 15, and so this gives us solutions of 3 and 5. These are the eigenvalues. Any questions? Once we have the eigenvalues of a matrix, we can use the eigenvalues to find the corresponding eigenvectors, which, as we know, will form a basis for the eigenspace. So the next thing I might ask you to do is to find a basis for the eigenspace corresponding to each eigenvalue. So next I would want you to find a basis for the eigenspace corresponding to each eigenvalue. This is the way I would phrase this question. In fact, I've seen this on a final exam somewhere. I give you a matrix and I say find, and the second question after you have the once you have the eigenvalues, I say find a basis for the eigenspace corresponding to each eigenvalue. And so what we want to do here is just solve the equation a minus lambda I times x equals 0 for each eigenvalue. So all we have to do here is to solve a minus lambda I times x equals 0 for each lambda. And for this, we're going to use the same thing that we always use, and that's an augmented matrix. We have a matrix equation. We're going to solve this with an augmented matrix. One of the things that I noticed is that once I started asking you to find coordinates, coordinates are just solutions to matrix equations, or vector equations. And a lot of you started to reject the augmented matrix as a method for solution. Don't do that. Just use an augmented matrix. I know some of you put an augmented matrix and then well, some of you just put the augmented matrix and expected me to read what the conclusion was. You have to connect the augmented matrix to an equation, and then you can write your solution. So let's go back and remind ourselves solving matrix equations with an augmented matrix. So for each lambda, I'm going to solve this matrix equation. So I'm going to start with, say, lambda equals 3. And so a minus lambda I times x, well, lambda is equal to 3. So I'm going to solve this equation. A minus 3i times x equals 0. I'm going to write the augmented matrix for this matrix equation. So I'm going to have 7 minus 3 and negative 4, and then 2, and then 1 minus 3. I'm going to emphasize that this is an augmented matrix by dropping in the zeros. I usually don't when I'm writing this out, but let's do that. This is an augmented matrix. And so this is actually equal to 7 minus 3 is 4, negative 4, and then 2 and negative 2. Notice that in between this first matrix and the second matrix, I can write an equal sign because these two things are actually equal to each other. Now we're going to perform row operations and get the reduced or echelon form. So I can't use equals because a matrix is not equal to its reduced or echelon form unless it started off that way. So equals is not the thing that I want to write. I'm going to say this is going to correspond to 1 and then 1/2 and then 0. And this first row will just wipe out the second row. So we get x1 is equal to -1/2, -1/2 x2, and x2 is free. We have to get free variables because we are looking for non-zero vectors. If we get 0 vectors, if I ended up with a pivot in each column of the coefficient matrix, then we have made a grave error. Then we've either subtracted something wrong, we've reduced things wrong, or we do not have the correct eigenvalue. I'm going to say that again because we have to learn how to troubleshoot. We have to learn when our matrix is clearly incorrect. If I got a 1, 0, 0, 1, that means I reduced the matrix incorrectly because we know that we should have free variables. We know that this matrix is to be not invertible. And if I get 1, 0, 0, 1, that means A minus lambda I is invertible. But that's not what we're looking for. So maybe I reduced the matrix wrong. That's the first thing that we check. Grab our calculator. Did I plug in all these signs correctly? If the signs are all correct and we still get this unique solution, which we're not supposed to have because x is to be a non-zero vector, then I got to go back and see, well, maybe I just subtracted things wrong. 7 minus 3 is 4, 1 minus 3 is -2. So if I did my subtraction correctly, then I got to go back and check my work on figuring out this eigenvalue. Maybe my eigenvalue is incorrect. And that means going back to my determinant of A minus lambda I and making sure that I did those calculations correctly. Any questions? One of the important things, one of the first things that we always learn in math classes is we learn to we learn some process for finding solutions. We also have to think about, while we're doing this, especially at this point in your mathematical career, how to troubleshoot things when they go wrong. And in addition to that, recognize when they've gone wrong. But in this case, we got free variables, which we expected. So I can say our solutions x look like x2 times -1/2 and then 1. If we don't like fractions, I can just multiply this by 2. And write it as -1, 2, if we don't like fractions. Actually, let me not write this or. We can multiply by 2 so that we have nice integers. And so this is a basis for the eigenspace of A corresponding to lambda equals 3. Any questions? Our other eigenvalue in this case is lambda equals 5, so we're going to have to solve that equation as well. So for lambda equals 5, I want to solve a minus 5i times x equals 0. So I'm going to write an augmented matrix. I'm going to be 7 minus 5, -4, and then 2 and 1 minus 5. And then I'll make zeros over here. This is equal to the matrix. 7 minus 5 is 2, -4, and then 2, 1 minus 5 is -4. These two are equal because I'm just subtracting on my main diagonal here. Not really a main diagonal, it's not square. I'm just subtracting on this main diagonal. That was cheating. And find the reduced echelon form. This first row is just going to be 1, 1, 0. And if I multiply by 2 and add it to the second row, that row zeroes out, which had to happen because we've got to have free variables. We've got to have non-zero solutions. So this says that x1 is equal to minus x2, and x2 is once again free. So my vectors in this case are going to be x2 times vector negative 1, 1. So a basis for the eigenspace of A corresponding to lambda equals 5 will consist of this vector, negative 1, 1. So if I multiply A times any multiple of negative 1, 1, I'm just going to get 5 times what we started with. We can check. So if I take A, negative 7 times negative 7, negative 4, 2, 1, and multiply it by negative 1, 1, we get negative 7 plus 2 is negative 5, and 5 plus 1 is 5. So we ended up with 5 times what we started with. So it all checks out. You don't have to type that in your answers. That's just me showing you that negative 1, 1 is in fact an eigenvalue, eigenvector of A corresponding to eigenvalue 5. Also, if I multiply A by any multiple of this vector, so like 10, negative 10, let's see, we end up with 50, negative 50. And that's just 5 times what we started with. Double check. You don't have to include your examples. It's a good idea to check, though, to make sure that you're right. Any questions? All right. Let's pause the video here because we know how to start with a square matrix. We know how to find the eigenvalues, and once we have the eigenvalues, we can find a basis for the corresponding eigenspace. This is a good time to pause the video and then come back and do some other examples.